Chemical Foundation of Life, Chapter 2, Part 6. Here we have our carbon atom. We've talked about carbon as one of the 4 key elements that's used to make organisms. But let's take a closer look at the actual structure of carbon and get a more sort of bird's eye view, or even closer, of why carbon is such an important element in the formation of organisms. If we take a look at the illustration at the top that shows us the electron cloud, we get a sort of rough idea of the orbitals and the shells in which we might find the electrons. Carbon has 6 protons and 6 electrons. But it's easier to understand how carbon is the foundation element in the formation of organisms if we use the orbital model that's illustrated at the bottom and take a look at the valence shell of electrons. So the first shell is going to have 2 electrons, but then the next shell will have the remaining 4, which means the valence electrons, there are 4 of them in carbon. We have the rule of octet for that particular shell of electrons, which means carbon's looking for or interacting with other atoms to make a complete set of 8. Basic statement: carbon can form 4 separate single covalent bonds, or it can form 2 double bonds. It can form 4 single covalent bonds with other carbon atoms. It can form 4 covalent single bonds with other atoms of different elements. And that's in fact exactly what it does. Because it has the capability of forming 4 separate single covalent bonds to fill the valence shell and to complete that rule of octet, we find that carbon is often described as a skeleton for the formation of macromolecules in organisms. One type of skeleton of carbon that's often described are the hydrocarbons. Hydrocarbons are long chains of carbons that are held together by single covalent bonds to which hydrogen atoms are attached. Notice in the illustration at the top, we have 4 carbon atoms that are attached to each other by single covalent bonds illustrated by straight lines. Attached to each carbon are some hydrogen atoms. For the carbons in the middle, to create those 4 single covalent bonds, we have 2 hydrogen atoms attached to each carbon. So here in the middle we have hydrogen attached to this carbon, hydrogen here, and then the 2 remaining covalent bonds to the carbons on either side. The terminal carbons have essentially 3 hydrogens attached for those 3 covalent bonds, and then the 4th covalent bond is to the neighboring carbon. So hydrocarbons, hydrogen and carbon atoms linked together. Well, gasoline, methane, which is natural gas, propane, those are all types of hydrocarbons. And captured within each of those single covalent bonds is an incredible amount of stored chemical energy. When we are able to break those chemical bonds, which for the hydrocarbons like gasoline, methane, and propane can be done by essentially striking a match and adding a little heat to the system, or fire, those hydrocarbons will release their chemical energy, again in the form of heat, with a tremendous amount of heat energy released. We rely on using that heat energy to power our cars and to power our furnaces. Industry, we rely a lot on releasing that chemical energy from the single bonds in these hydrocarbons. If we take a look at hydrocarbon, we call them chains. So these long strands of carbons to which hydrogens are attached are illustrated in these 2 space-filling models of types of hydrocarbons. They actually shouldn't really be quite this sophisticated, perhaps. You might say, what are those red things on the end? Well, we'll talk about the red things on the end in another section. But let's focus on the long chain of carbons, which are illustrated by black, and then the hydrogens that are attached to the carbon atoms, illustrated in white. Notice that the long hydrocarbon chain on the top is straight, and the one below it is bent. Well, that's because we don't have single covalent bonds all the way down along the chain in the second lower illustration. In sort of the middle of that hydrocarbon chain, for what's called oleic acid, there is a double bond. And that double bond causes that long hydrocarbon chain to bend, or have sort of this little sort of kink in the hydrocarbon chain. When that happens, we're going to find that those types of hydrocarbons are most likely to be in a liquid form that we call an oil. On the other hand, when we have single covalent bonds between all of the carbons, then there's a good chance that that particular hydrocarbon might have a little bit more solid nature. Just depends on the hydrocarbon. If the carbons are essentially on one side of a double bond compared to the other, so sometimes scientists describe where the location of the hydrogen ions are, or the hydrogen atoms, I should say, attached to a hydrocarbon chain. So if we have all of the hydrogens on one side of, or the same side, is often described as a cis configuration. And when we talk about hydrogens attached that are on opposite sides of a double bond, and we call that a trans configuration. We're going to describe this in more detail when we talk about trans fatty acids. And so we're just introducing this concept of cis configuration and trans configuration, and we'll remind ourselves when we get to the point where we're talking about trans saturated or unsaturated fatty acids, or cis saturated or unsaturated fatty acids. This is what we're describing. Where's the double bond, and where are the hydrogens attached to the carbon chain? Another concept that has to do, in some cases, with molecules and macromolecules. And since those molecules and macromolecules are made out of carbon, or based on the structures of carbon arrangements, and that's the idea of isomers. Notice that we can have a chemical structure or a molecule that has a particular number of atoms of different elements, like butane and isobutane, illustrated at the top. Butane and isobutane have the same number of carbons, same number of hydrogens, but if you take a look at the structural formula, or the arrangement of those atoms, they're very different for the two molecules. When we have the same chemical formula, but different structural arrangement of atoms, those are called isomers. And if the arrangement is simply a divergence or difference in arrangement, we call those structural isomers. If we have a double bond somewhere within that structure, and we have the arrangement of certain components of those molecules on different placements or different sides of that double bond, we call those geometric isomers. So we can see in the illustration of cis-2-butene and trans-2-butene that a structure that we call a functional group called a methyl group, if the methyl groups are on the same side, we call that cis-2-butene. If they're on opposite sides, we call it trans-2-butene. Again, that brings back that concept we just introduced in the previous slide about cis and trans. And it's important especially for chemists, but for some concepts of discussion, we do need to include a little bit or have a rough idea of cis versus trans when we're talking about biological systems too. And then we might have molecules that are mirror images of each other. Those are called enantiomers. Mirror images are like as if we were to place our hands palm facing one another. So take your left and your right hand, put your palms together, and realize that your hands are mirror images of one another. And that's why we have right and left hands. The same thing can be true of different isomers. The L isomer on the left and the D isomer on the right, if you were to try to overlap them or see if you could get them to essentially fit into one another, it really wouldn't work when you're using a real three-dimensional model. It seems like when you're looking at it, it should, but if you use Tinker Toys or actual physical models of these molecules, you'll find that it doesn't overlap. So it's hard to illustrate enantiomers in a two-dimensional picture. It works much better sometimes for students to actually see these mirror images in a three-dimensional model, and that's why using your hands as an example is sometimes a good way to show students what mirror image enantiomer isomers look like.